So we have today 39 people, which is quite a good number. And what I'm going to do is I am going to start sharing. Thank you for joining. I hope you have been enjoying this course so far. And what we are going to do is we're going to discuss the last topic, which was an application of open quantum systems to spontaneous emission. So let me go through this slideshow. It always takes ages from beginning. Somehow there is some issue with regard to PowerPoint and Zoom, and I don't understand. So we're going to talk then about the final lecture, which is associated with how you apply the dynamics of open quantum systems that we have seen so far to spontaneous emission. And afterwards, something I always like to do every time I'm teaching a course. Some of you may have seen my courses in the past. I don't know if you probably realized or not. If time, and normally time permits, I like to show how you use whatever I'm teaching real life situation. And this tends to be quite useful for people. And that's what I also intend to do today. So if you want to have a look, all the asynchronous lectures are at UCL Physics and Astronomy 0069. By now, imagine you know the hashtag. Things are also available on Dropbox for the intercollegiate people. I intend to put everything on YouTube over Christmas because I'm going to have a bit more bandwidth. But I hope you all have been able to join so far. So to start, we're going to assess where we are. We're here, right? So we have seen all this. This was an experimental course also for me. It's the first time I'm doing this online. So I didn't have any idea how long it would take, how much time and effort. So I was thinking about 10 or 11 weeks. So we're going to close in week 10. And in fact, I am somehow relieved because I understand that there's going to be absolute chaos in the next week with people traveling and going elsewhere. So I can say that I'm relieved that everything is going to be okay this week. And I have a few announcements. The deadline for problem sheet 2 is today. If you have stories would like to make use of that, drop me an email to remind me. But then in this case, you have a week. And for those who have done so, thank you so much. And what we're going to do then is to have a look at problem sheet 3. Actually, is available today. The deadline is the first day of second term, which in fact is 11th of January 2021. So you have plenty of time to do it. And to start what we are going to discuss today, this is an application of the Lindblad form of the master equation. So what we do and what we covered partially also in the previous lectures is you get a phenomenological expression for open quantum systems. You assume that you have Markovian dynamics, meaning that the evolution of your system just depends on the evolution of your system in the previous instant. and that your environment is not providing information to the system, only the system to the environment. So there's not information flowing back, and it's kind of one directional. And this, if you make these assumptions and you also assume some form for your coupling in terms of jumping operators, you can write an effective Hamiltonian, which is given in this form. And you can see that this Hamiltonian is non-Hermitian, and it depends on what we call jump operators, and jump operators are operators which are associated to this coupling with your system, with your environment, I mean, because we have a system and we have an environment. That's why we need sometimes to treat the system as an open quantum system, because many times you don't know what the environment is doing, but you can make some educated guesses and assumptions. And I left some exercise for you to try, which you can give it a try. I provided already the solution last lecture. And the application we're going to see today, which is lecture 10, there is given in much more detail. We can watch the video, is the spontaneous emission for a two-level atom. So we have a system, and the system has an excited state and a ground state, and both are separated by this energy here, h bar omega A. And pretty much what is going then to happen is that we are going to assume for simplicity that the energy of the ground state will be 0. And the energy of the excited state is h bar omega A. So there's a question. So the information about the environment is always contained in the jump operators. Yes, it's always contained there. And it is a good question, because what in fact is that you can use this to make educated guesses. For instance, sometimes you don't know how the environment is going to behave, but you can see what is happening if it's leading to decay, if it's leading to loss of energy, if it's making some system go from one state to the other. And then you find a way of incorporating this. Another way, which would be more rigorous, would be if you trace out the environment. Say, sometimes you can write the whole Hamiltonian, but you cannot solve the whole Hamiltonian. So a possibility would be to write then the whole Hamiltonian corresponding to system and environment. Then you trace out the degrees of freedom associated with the environment. And from there, you are going to get a similar expression than the one that we have derived here, which, for instance, in quantum optics, this is an example that I'm going to do today and that was done in the asynchronous lecture, is very, very typical for quantum optics. And if you want to see it done rigorously, get a quantum optics book and have a look at the Wigner-Weisskopf theory, because that's how you do it properly. But this heuristic method that we are seeing is also quite useful, and you can get a lot of information from it. And you see how much, in fact. If you watched the asynchronous lecture, I do everything derived up to the last epsilon, but here I'm going to provide an overview. So, yeah, it's not moving because I was in the chat. So the energy of the ground state will be 0, and the energy of the excited state, that h bar omega A. And we have a jump operator. Now it's coming, everything comes at the same time. So the Hamiltonian then is given by this expression. So you have here the energy of the ground state, here the energy of the excited state, and then you have h bar omega A E, because for simplicity, we assume that the ground state is 0. And if you look at this jump operator, you have a gamma. And then you have this guy, which is cat chi bra e, and this is going to be associated with the rate of spontaneous decay, this gamma here. And this operator is going to do the following: is going to make the system jump from the excited state to the ground state, which is something quite useful for us. So if we compute the effective Hamiltonian, pretty much what you have to see how these things are going to work when you use the expression that we have seen in the previous lecture in terms of Lindblad, of the Lindblad form of the master equation, and in terms of the jump operator. So you can see here L dagger L, which has to be there, and since we have just one jump operator because we are considering one two-level atom, you are going to find this kind of expression when you have modulus square gamma. Here, I'm going to use orthonormality, so this is equal to 1, and you end up with some expressions which have a projector onto the excited state. And one interesting point is you can you see that there has been a shift in this energy, because we know that the energy of the excited state is h bar omega, right? Now you have as if this energy had a complex part. And this is very interesting. I don't remember if you remember what I said, like in lecture 0 or 1, one of the very first ones, that when you're considering an effective Hamiltonian, sometimes if you have decay, this can be non-Hermitian, and this would lead to eigenenergies that are complex. So that's pretty much what you're seeing here. And this becomes even more obvious if you would see how HF would apply to the excited state. Now, you can also have non-Hermitian Hamiltonians with real eigenvalues. I'm not going to see this here. Actually, after unitary transformations, you would be equipped to know how this whole thing works and the modified inner products. So I may become creative at some point. It's quite interesting for that, but it's not something I'm going to cover in this lecture or in this course. And the imaginary part of the energy here is associated with decay. So this is quite an important point, because that's how decay starts to appear in the presence of this type of Hamiltonians. So we have then a master equation, which is given by this form. So you have one part which is related to the effective Hamiltonian, and then you have another part which is that one where you have that sum of the jump operators, which in this case is just 1. I mean, two-level atoms are useful because of that, because they simplify your problem a lot. And for instance, if you have a 3-level atom or 4-level, you could have constructed jump operators to make these things decay to the ground state or whatever you want it to decay, but it would be definitely more complicated. And we consider that the atom is initially in the ground, in the excited state. Could be a coherence superposition, but we want to simplify things. So the evolution is described by this form, and actually this is something that is not that trivial, but it can be shown that if you have this excited state here as initial state, you would have that the density operator terms associated with the crossed terms when you have not these projectors E, G, G, but when you have the operators E bra and G cat, or the other way around, that they would be 0 for all time, which is very convenient for us. You can try to show, it's good exercise. And if you insert this in the master equation, you end up with this expression on the for that part where you have the effective Hamiltonian. This is what you have considering the jump operators and the coupling with the environment. You see that the coupling in the with the environment is present in two places. It's present here because you had to consider also jump operators there, and is present here in this remaining term. And here, that's what I'm going to refer to once more. You can clearly see that you have an effective Hamiltonian. And if you apply this to the excited state, you get this shift. Can you see? This is like an eigenvalue equation, guys. So that's why we consider this as if you were putting a width in the energy of the excited state. Is there a physical interpretation for this? The physical interpretation is we were clever. We have set the energy of the ground state to be 0. And we constructed our jump operators in such a way that we are only allowing for a jump from the excited to the ground state. So this means that decay is only happening from the excited to the ground state, and is where we set up our energy to be 0. So that is pretty much the interpretation, that you have this effective Hamiltonian. The part that makes the Hamiltonian effective is in fact only associated with decay from the excited to the ground state. In fact, this name jump operator is quite nice because it's making the system jump. And on top of that, this is giving you 0 because you have chosen the energy of the ground state to be 0 just for the sake of simplicity. And then another question, would it be possible to give a few hints on how we can show that the cross terms are 0 in the density matrix? Well, the hint is you are probably going to get some differential equation, okay? So if you write everything with the cross terms and everything, you are going to get some equation in terms of the density operator, right? And then on the left-hand side, you're going to have things which are going to be Rho EE dot projector EE plus Rho GG dot projector GG. And then you have all the rest on the right-hand side, because that's on the right-hand side, that's where you apply this for operator. So to solve that, you have to know how you are going to sandwich with bras and cats. And probably, because you don't have anything on the left-hand side for the initial conditions that you are assuming, you are going to get things, say, you can see immediately that Rho GE dot and Rho EG dot are going to be 0 because you don't have anything, right? In this case. Or you could not know, hang on, I'm saying rubbish because you would have Rho GE dot and Rho EG dot as well, because I'm not making the assumption that it is 0. So what you would start is get all the complete thing, which would give you then 4 differential equations if you know how to sandwich from E to G from one side and to the other. And then applying the initial condition, you're going to see that in one case, you are going to get that some coefficients have to vanish. So pretty much, I started from the wrong assumption. So let me go back. Now it's going to go berserk. It always does when I go back. So I'll take care of the other ones. So in general, are the eigenvectors of the non-isolated system the same as in the isolated system? Yes, because you are not considering I mean, in reality, I'll go back and explain this matrix, okay? But it's because things get crazy when I go back. So let me go for the second question before. So in general, are all the eigenvectors of the non-isolated system the same as in the isolated system? Well, in reality, we would have a compound system, right? So what we are doing is we're not solving the problem rigorously, because system plus environment would be a compound system. So you would have a basis for the whole thing, but we are tracing out the environment. So effectively, what we are doing is we are solving the problem in the basis of the eigenvectors of the isolated system, but we are incorporating the environment via these effective terms. Okay? So would you be able to clarify why we can associate the imaginary part of the eigenvalue with a finite width of the excited energy level? What is going to happen is, for instance, let's say you would, like what we have done, you compute some transition probability from the excited to the ground state, or you would compute, okay, how does this look? Even if you want to first order perturbation theory, what you're going to see is that this gamma is going to make whatever probability you have wider. So you're going to have something that is going to look a bit like a Lorentzian. And what is going to happen is this is going to depend on this gamma. So this gamma is contributing to make whatever, if you try to determine a shape for which this transition can happen, is going to be wider if it were not present. So you have what you call line broadening, and this can be incorporated via this complex term. This is something, for instance, if you're curious, have a look at quantum optics books, or books on spectroscopy. Books on spectroscopy, they're more hand waving. So if you really want to know this well, have a look at quantum optics books, because this gamma is going to lead to your line corresponding to that specific transition being wider. And that's why you can see that this complex part is leading to some kind of broadening. And there was this question that someone wanted a tip, right? So let me go back, because we started saying, yeah, it's going to take a while, and then it comes back at the same time, everything. I don't like this. So we started by saying that the evolution was described by this whole T, right? And that actually you would still have other matrix elements if you write this in these two-state bases, where you have Rho EGT, Rho GET, and then the operators here where you don't have only the projectors, you would have GE and you would have EG. And I said, okay, to show that, you had to start by constructing the time-dependent Schrodinger equation. So we have this master equation, which is equivalent to our time-dependent Schrodinger equation when you have an open quantum system, right? So it's a generalization of, actually, if I'm precise, von Neumann equation to open quantum systems, to put the environment in there. So what I would do is write the whole thing, not only with these two terms. Here I'm kind of simplifying the thing. Write for the left-hand side, write for the right-hand side, and then you're going to get something which, if you sandwich from the left and from the right with G, E, E, G, and you have to choose it cleverly, going with brass and cats from one side or the other, you're going to be able to release all the equations which are related to Rho EE, Rho GG, Rho GE, and Rho EG, the four. And if you assume that at the very beginning, you are going to have EE, you are probably going to get to some equations which for the cross terms, this has to happen, okay? That are only going to make sense if they vanish for all times. So that's how I would start. If you look in the asynchronous lectures, you're going to see that we have a derivation for the diagonal terms. And that derivation is quite useful because you can see that you can release these guys and you can calculate how they vary as a function of time by coming from the left and from the right with the right bras and cats. So that's what I would do. And I think it's fiddly, but I don't see it being difficult because you should get this from your initial conditions. And here we have the jump operator. So you can see, someone is. I see, I'll try out again this way. What quantum optics of which authors we recommend? So 2 questions. It depends on what you like. If you like more applied, if you like more mathematical. For instance, one quantum optics book, which I think is quite complete, is this Born and Wolf, is quite nice. But it is pretty much what you want to do with that. When people ask me about recommendations related to books, it's always the issue, what is that you want to do with that? Because some books are better for one thing, other books are better for something else. So you need really to have this kind of information. Okay? So if we come back to this, and you can see this jump operator is making the system decay. Here there is nowhere to decay. So apply the jump operator, go to 0. Here you apply the jump operator, you have gamma G. So you go from E to G, and that is the idea. For instance, if I wanted to construct something with 3 levels, I would put 1 decaying from E2 to E or E2 to G, depending on what transition rules are allowed and what is forbidden. And would do the very same thing. Because sometimes it's forbidden, sometimes you cannot decay, physically speaking. And if you substitute these, this is what I was saying, have this here, the right-hand side, left-hand side, sorry, and here is what you get for the right-hand side. And if people want to try it with the cross terms and you want to do with everything, you get here 2 more, and here you have also some more. And then you just have to see how you sandwich things. Move. Doesn't move. Doesn't like me sometimes. Okay, now it's moving. So you see, that's what I was talking about. If you multiply from with the right bra from the left and with the right cat, you apply the right cat from the right. Multiply is like multiply, okay? Multiply is a bit hand waving. What we are really doing is we're applying the bra from the left and the cat from the right. So then you get this expression, which is a first order differential equation, which is easy to solve. You see, you have gamma EE dot T, and here you have gamma EE, and you have this minus gamma whole. I keep on changing these letters, okay? So you have whole dot EET. Here you have minus modulo square gamma whole EET. And you can solve it, right? And you also know the initial condition. This is done also in the asynchronous lecture, and then you can see that you have then whole EE0, which leads to this expression. Now I know this, so I can go for the other one. I multiply G from the left and from the right. So you don't multiply, this is nasty, okay? Just say like this, but what you're doing is you're applying the bra from the left and the cat from the right. Sandwiching is also as nasty as multiplying, but anyway. So you know what I mean. So when I do this, I get this whole GGT, and you have also gamma square, whole EE, and we have the expression for whole EE. So if you solve it, you get whole GG is 1 minus x minus gamma squared T whole EE 0. So you can see that these things are decaying, right? Here, the whatever you have in the excited state, or the probability that you make a measurement in the excited state is going to decay. If you remember how density matrices and density operators are defined, you have probability that something happens, and then you have the projector, right? And here we have just what we would have as a coefficient for the excited state. So you can see that the probability that you make a measurement in the excited state is decaying with time, and the rate is minus gamma square. And here you see is 1 minus this for the other case, which makes sense because you have a two-level system. So whatever is happening on top should be compensated for what is happening at the bottom, meaning here top and bottom excited and ground states. So the probability of measuring an atom in the excited state will decay exponentially in time with this rate. So for the curious, you can derive this rigorously instead of using phenomenological arguments, using the Wigner-Weisskopf theory. One thing that is interesting is that here we make all these assumptions, but we put by hand gamma via the jump operator, right? We don't know what gamma is. So maybe if we solve this rigorously, we would be able, okay, it would be more cumbersome and it would be also operate Hamiltonian independent, but maybe we could have derived an explicit expression for gamma. So this is, you gain on one side, you lose on the other side, and life is normally quite very much like this. So actually, just to close this, we can construct master equations phenomenologically by identifying the system Hamiltonian. We can also identify the jump operator corresponding to irreversible dynamics due to interaction with the environment. And for examples of jump operators and use of master equations, for instance, you could have, people do educated guesses at the end of the day. So you could have, for instance, randomly varying magnetic field and spin. So basically you have some kind of classical randomness and you have a spin quantum states which are mixed by this classical randomness. So you have to make it jump somehow, and you have some rate which is associated with this jumping process. Or you could have a cavity which is leaking, because in reality, when you're performing measurements and you have a laser cavity or whatever cavity that you have, you cannot capture photons indefinitely. So eventually they're going to leak. And this process is mathematically equivalent to having a damped oscillator. So you have to think, okay, what do I have to do then? Then you have to consider that you have a jump operator, which is proportional to a photon annihilation operator, because you're going to annihilate a photon. So, and so on and so forth. So you can use this, is very powerful. You can use this to construct a lot of models, especially for things you don't know. So there are more applications. For instance, noise, in quantum information problems, you find those who are working on that, you find this a lot. You have quantum effects in nanostructures, you have energy transfer biological systems, and so on and so forth. So as far as the syllabus is concerned, I want to thank you for your attention. And what I'm going to do next, because I think is quite interesting, is I'm going to bring, and we're going to have time for this, some research talk in which we are going to see some aspects of what we have covered here. not explicitly, but they are used as tools to construct some theory, and it's some research in which I have been involved. So it's pretty much, you know, when people say, show me what you've got, or how do you use this kind of thing? And it's useful for people to see as someone has some chat. I have a question. Okay. Slightly off topic, I have a question concerning von Neumann's equation for the evolution of density matrices and the Heisenberg equation to calculate the time evolution of operators. They have a difference inside. Is this correct? Actually, this is a good point. I've never thought about it. I don't see why you should not compare, but we need to do some extra thought to think why the sign is different. I don't know, like, just like that to explain you, but thank you for making this point, because I think it's an interesting one. It's going slightly off topic. I have a question regarding von Neumann's equation for the evolution of density matrices and the Heisenberg's equation to calculate time evolution of operators. The two expressions have a difference in sign. Is it correct to compare these two expressions, since density matrix is also considered an operator? It's correct. Difference in sign, I don't know from the top of my head where this comes from. My gut feeling would tell me, if you want to make a comparison, look again for what is implicit, what is explicit, because this could give you the answer, and put both derivations side by side and see what kind of assumptions are being made. Because normally this gives you a hint of, okay, what is that I'm taking into consideration here, here, or there. But I really don't know from the top of my head. So I'm gonna start record. I stop recording and then I'm going to restart the recording, because what I'm going to do now is I'm going to cover some research. Very good. The difference in sign goes away as is 1 minus divided by minus I is equal to I. Okay, so it's probably pretty much the same then, because rho is an operator. But it's good to have a look. I wasn't dividing anything, but it's right, because, but you have 1 divided by I bar, or minus 1 IH bar. You need to see the equations in your head. Thank you, Alberto. That is very nice. So let me stop this.